It's a great honour for me to have been asked to give this IPEM lecture, especially since it's a John Mallard lecture. John, indeed, as you alluded to, was a real pioneer in our field of medical physics. Here he is, photographed after receiving his OBE in 1993. I had the great fortune to actually work with John in John's department from 1983 until John's retirement in 1992. And he was not only my boss, but my mentor during that time. So I really owe my career in medical physics to John Mallard. So it's a real pleasure to be able to give this lecture named after him. So just a few words about John, actually. So John was appointed to the chair of medical physics at Aberdeen University in 1965. He was the first holder of that chair. His desk always looked like that, by the way, with piles of papers. He really was a pioneer in our field, in many areas of our field, particularly imaging. In 1969, he and the team at Aberdeen developed the world's first digital tomography system. There had been analog tomography systems before, but they developed the world's first digital tomography system, the Aberdeen Section Scanner, or AS, wonderful name. That's the AS Mark I scanner there, and it produced tomographic scans of the brain like that, and the body too. Incidentally, my first exposure to medical physics actually was as a so-called summer student, nowadays it would be called an intern, I suppose, in John Mallard's department in Aberdeen. So I was doing my physics degree in Aberdeen, called natural philosophy at that time, and I developed a contact with the department, and I worked as a summer student there for 2 summers in the mid-1970s. And it's hard to believe now, but the first summer I worked there, I was actually operating this machine on patients. I had no qualifications at all, and clearly no straight registration or anything like that, but here I was scanning patients every day on this scanner. But it was fantastic because it exposed me to real medical physics, and it really cemented in my mind that medical physics was what I absolutely wanted to do. Incidentally, that's me around that time. You can see how hardly changed at all. Anyway, John went on to lead a team working on magnetic resonance, and this was now with Jim Hutchison. And Jim built all this equipment to image by NMR, imaging a mouse in 1975. That's the somewhat famous in MRI circles, the famous Aberdeen mouse. And they then went direct from mouse to man at John's insistence, and this led to the building of the Mark I MRI scanner. There's Jim Hutchison standing beside the bare magnet in about 1977, and spin warp imaging was invented on that system, and the world's first ever diagnostic MRI scan was performed there in Aberdeen in August 1980, and that's one of the first diagnostic scans showing tumours in the liver. So John Mallard was absolutely instrumental in all of that happening. I joined in 1983, joined the NMR imaging group, because it wasn't called NMR, it wasn't called MRI yet, still had the nuclear word. I joined for 9 months, in fact, in 1983 and stayed for 36 years. So that's the group in 1984. There's John Mallard, there's Jim Hutchison, and there's me at the end, sporting a prototype Scandi Noir jumper. And that's me again, lying there pretending to be a patient in the Mark I scanner with John there. John really was instrumental in guiding my career. For example, in 1986, he suggested to me that I look into double magnetic resonance to see what that might do. And that led to me working on double magnetic resonance method, including ESR and NMR at the same time, which ultimately led to the research that I'm going to speak about today. This is the most recent photograph I have of John, in fact. There's John sitting at the front there. This is in April 2016, when that was at the opening of the Mark I MRI scanner exhibit, because it's now permanently on permanently shown in Aberdeen Royal Infirmary. That's John, that's Jim Hutchison, Tom Redpath, Peter Sharp, and myself. That's, I'm not sure what the collective noun for professors is, but that's a gaggle of medical physics professors there. Okay, so on to the topic of this presentation, which is fast field cycling MRI. Don't worry if you've never heard of it. I'm going to explain what this is about and how it can potentially be of benefit. So the structure of the remainder of the talk is as follows. So I'll describe the basic concept of FFC MRI. I'll explain how it works. I'll show some hardware in addition to this slide. And I'll show some ex vivo and clinical results at the end of the talk. Okay, so standard MRI, just a very brief one-slide recap of how standard MRI works. So in standard MRI, we have a strong magnet, typically 1.5 or 3 Tesla, and that aligns the magnetic hydrogen nuclei in water along the horizontal direction of the magnetic field. Then the scanner sends in pulses of radio waves at the right frequency, 64 megahertz in a 1.5 Tesla scanner, and they give the nuclei extra energy and, in a way, nudge them out of alignment with the magnetic field, sets them precessing. And after a delay of about half or 1 second, the nuclei give up their extra energy by emitting their own radio wave signals, which are picked up by the scanner and used to generate the high-resolution images that we're all used to seeing. So that's a very short summary of how standard MRI works. This delay time between the pulse going in and the signals coming out is called the T1 relaxation time. And it's always been known, really since the very start of MRI, that this is very important in encoding diagnostic information into MR images. Because the T1 relaxation time, the delay time, the response time of nuclei depends on the disease state of tissues. So the T1 tends to be longer in diseased tissues, cancer, for example, than it is in normal tissues. And you can encode those differences into the intensity of the images in a T1 weighted image, for example, and that is very useful from a diagnostic point of view. So that's been known since the start of MRI. What's less known, even in the MRI community, is that the way in which T1 changes with magnetic field, and that's called T1 dispersion, can also be a marker of disease. So this is known because in various labs around the world, people have taken small samples of tissues, normal tissue and diseased tissue, from animals and indeed from excised human tissues from surgery, and they've measured how the T1 relaxation time of those tissues changes with the strength of the magnetic field. Now, you can't do that on a standard MRI scanner, but you can do it on a laboratory NMR instrument if it's set up in the correct way. So these studies have shown, over decades in fact, that T1 dispersion, the way in which T1 changes with field strength, could be a useful biomarker, a useful marker of disease, if only you could measure it. But you cannot measure it in a standard MRI scanner because each scanner only works at its own native field. For example, 1.5 Tesla, 3 Tesla, or if you've got vast amounts of money, you might have a 7 Tesla magnet. They're all excellent instruments. They produce high resolution images, but they only work at their own native field strengths. They cannot measure T1 dispersion by definition because they operate at fixed field. Nevertheless, that was our idea about 7 or 8 or 10 years ago. We decided we wanted to build an instrument that could measure T1 dispersion in vivo, potentially in patients, and use that as a completely new marker of disease. So there we have a cartoon with a labeled dispersion MRI. We'll come later to see what these instruments actually look like. And the idea is that you have the patient inside the scanner, and in a spatially resolved way, you measure a graph of T1, or in this case, 1 over T1, as a function of magnetic field strength. And in normal tissue, that might just be a curve like that, whereas in diseased tissue, the curve might be at a different height and a different shape with even some structure in it. So the idea is to use the shape and position of these T1 dispersion curves as a marker of disease. So the shape is a marker of disease, as it says. So to do this, we've built scanners that we'll see later in the talk, and we've used them in measurements on normal and diseased tissues, and indeed that's what the scanner looks like, and those are the kind of results that we obtain with different curves for normal and diseased tissue, and we've started to image patients as well. So that was the preamble. So how does this work? What's the basic concept of FFC, MRI, and dispersion imaging? So how could you go about measuring T1 as a function of magnetic field? There are really three potential ways of doing that. If you were very rich and had an enormous amount of space, you might think, okay, I'll just buy 100 MRI scanners, each one has a different field strength, and we'll do it like that. So you invite the patient into your enormous cavernous scanning center first thing in the morning, and you set them up on the 0.01 Tesla scanner, and they're in there for about 20 minutes collecting images, and then they think they can go home. No, sorry, you've got to do this another 99 times, because we're going to do this at a range of field strengths, 100 field strengths. So the patient ends up being there all day or all week, I don't know. But so clearly that's not a practical way of doing it. Second potential way of doing it, measuring T1 as a function of field strength, is to buy one instrument with a variable magnetic field control, if such a thing was available. So there you have a scanner with a magnetic field control on the front, and you set the patient up once, and then you collect an image at the first magnetic field, and then a Monty Python hand comes in and changes the magnetic field to a different value, collect another image, and so on, and you do that however many times however many fields you want to explore. That's more practical than the first option, but still it's rather difficult technically. Among other things, the radio frequency coils would have to be retuned at every different field strength because the frequency would be different. So potentially possible, but not ideal. The third potential way of doing it is to use magnetic field cycling, as you might already have gathered from the title of the talk. But first you have to build the equipment, because you cannot buy a fast field cycling MRI scanner from any manufacturer, at least not yet. So how does this field cycling method work then? A bit more detail about how it actually works. So in field cycling MRI, the magnetic field is switched between 2 or sometimes 3 levels during the pulse sequence. While the patient's in the scanner, we switch the field up and down. So it's a bit like this. Here's a graph of magnetic field as a function of time, and the field is going down, up repeatedly. So that's the basic concept of what we do. So just to reinforce this, we have part of the experiment at low field. That's a low field. And part of the experiment at high field. There's a high field because there are mountains in the background. For any MRI aficionados in the audience, you can also tell it's a high field because of the polarization of the cows. They're all pointing in the same direction. So we have 2 fields in one scanner, in other words. So at low field, we have the relaxation taking place, and at high field, that's when we do the detection of the signals and application of the field gradients. So in a slightly more technical way, here is a field cycling pulse sequence diagram, or at least the part that pertains to the magnetic field strength. So there's magnetic field against time. So we have 3 parts. So we have a polarization period at high field, where we polarize the spins. Then we switch down to the field at which we want to measure T1. That's usually a lower field. And at that time, during that period, relaxation takes place. The duration is about the same as the T1 relaxation time, about half a second or so. And then we switch rapidly up to the high field again. That's when we measure the signals and apply the magnetic field gradients for spatial encoding. And then this whole thing is repeated a number of times to cover K-space to collect the image data. So the NMR signals are always read out at the same magnetic field strength, the same high magnetic field strength, so we never have to retune RF coils. Nevertheless, we can switch the evolution field to a range of different values in order to explore T1 as a function of field strength. That's how that is done. The field ramps, by the way, are short compared to T1, and that's what gives the name fast in the fast field cycling. What do the scanners look like? Not like these bathing huts in the Murray Coast. The scanners, it's not yet possible to buy an FFC MRI scanner. So we have indeed built our own scanners. We've built 2 prototype whole body scanners now. Most of the scanner architecture and hardware is actually the same as for a normal scanner, except for the magnet, as you might expect, which is very different, and the magnet has to have its own rather special power supply as well, which is also different to anything you'd find in a standard scanner. But everything else, the gradient control and so on, is pretty much the same, and the RF chain is pretty much the same. So here's our latest prototype scanner that we've been building for the last 7 or 8 years. It does look rather different to a standard hospital MRI scanner, but there are similarities. So there's the magnet. Underneath this green potting is a resistive magnet with a maximum field of 0.2 Tesla, so it's low field. It takes 2,000 amps of current through the solenoidal windings in order to generate that field. The bore across the scanner is 50 centimeters, so it's moderately tight, and it's rather long as well. It's 2 meters long, so it's not for the claustrophobic. This scanner also has these structures here, these gray coils, which are environmental field correction coils. And we send currents through those to cancel out the environmental field, including the Earth's magnetic field in the vicinity of the scanner, allowing us to set the field down almost to zero magnetic field during the evolution period if we want to do that. So ultra-low field imaging is possible by that means. And then there we have a head RF coil tuned to 8.5 megahertz, which is the Larmor frequency at 0.2 Tesla. The scanner has been built as being suitable for patient studies, and it has a communication system, music system even, panic bulb, airflow through the bore, and in-bore lighting, all those things that make it relatively comfortable for volunteers or patients. We build all our RF coils ourselves, so there's 3 versions of the head coil. We now use 3D printed formers for all our RF coils. There's an openable hinged knee coil. There's a breast coil with its covers removed, and there's the breast coil in place with some test objects in it prior to scanning. These are images of volunteers, so there's a brain at its full field. There are knee scans and breast scans, one at 200 millitesla, 0.2 Tesla, and one at 0.001 Tesla evolution field. And despite the amazingly low field of this scan, you can see the image quality is actually not that bad. Not as good as 3 Tesla, of course, but you wouldn't expect that. But nevertheless, you can see all the structures quite well. And you can see that the image looks different at 1 millitesla compared to 200 millitesla, because T1s and the T1 distributions are different at the ultra-low field. So I'd like to explore now some clinically related results from our system. So the first clinically related results I'd like to look at are in osteoarthritis. So here, patients undergoing joint replacement surgery agreed to have FFC measurements made on their joint tissues after the tissues had been removed. So after surgery, they agreed that their tissues would be examined by fast field cycling methods. So there's an excised joint. I think that's a hip joint, a ball of the hip joint. So a core was taken, about a 1 centimeter diameter core was taken of the cartilage, and then that core was placed in a sample tube. And that was placed in turn in a benchtop device that we have in our lab called a relaxometer. So this is a device that has a magnet in the right-hand box there, and that's the rest of the electronics. This does not produce images. It just produces graphs of T1 versus magnetic field strength, T1 dispersion curves, in other words, of anything that's in a test tube inside its magnet. So it's for small tissue samples. And these are the graphs that we obtained from cartilage, from normal and diseased cartilage. So the healthy cartilage generated the curve like this. So this is from healthy cartilage, and that's 1 over T1, called the relaxation rate, as a function of the evolution field strength as the Larmor frequency. And it has these bumps here, which I'll come on to in a minute. And you can see that the curve from healthy cartilage is different to the curve from osteoarthritic cartilage. So you can see that the levels of the curves are different, the heights of the curves are different, there's an offset between them, and also the shapes of the curves are different, the slopes are different. Furthermore, there are these bumps here, and they're called quadrupolar peaks, and they only show up in tissues where there is immobile protein. So, and if you look at those in detail and fit the curves to Lorentzians, then we actually see that there are subtle differences also in these quadrupolar peaks in this region. And this is all at ultra-low magnetic field strength. So this is all below 0.1 Tesla. In fact, that's where the interesting differences occur. You can actually see here, even in these curves, that the curves are actually tending to the same value. So if you made measurements of T1 at normal field strengths, 1.5 Tesla or 3 Tesla, you would actually get the same T1. Whereas at ultra-low field, these curves are indeed quite divergent. So that gives us hope that these differences in T1 dispersion curves are indeed potentially diagnostic. The next disease I will look at is breast cancer. So again, we had ethical permission, of course, for this study, and a small number of patients who had had mastectomies for breast cancer agreed to have their tissues examined ex vivo, but in the same way, using our benchtop relaxometer system. So again, the mastectomy tissues were taken, and they were small samples were taken from those. About 1 milliliter samples were taken and put in test tubes into this instrument, and we were able to examine the tumor tissue. So this is from the center of a tumor, and it generated a T1 dispersion curve like this when plotted on a log plot like this. So it produces a linear plot, again with these bumps, these quadrupolar peaks. That is in very distinct difference to the normal tissue. So this was tissue well away from the tumor in the mastectomy tissue, and you can see that the normal tissue looks very different. So it's piecewise linear this time. So there's a linear section there, and there's a linear section there with different slopes, and there's no indication of these quadrupolar peaks occurring in the normal tissue. So we thought that was quite exciting, because this definitely shows a very distinct difference between the tumor and the normal tissue in terms of the shape and the locations of these T1 dispersion curves. This definitely gives us hope that we could use this information in vivo in patients. But perhaps what was even more exciting was that when we took a sample of tissue from the periphery of the tumor, this was tissue that even looked visually normal, the curve looked much more like the curve from the tumor than it does from the curve of normal tissue. So this is tissue that's becoming fibrotic, that's becoming cancerous, beginning to become cancerous at the periphery of the tumor. So potentially this is also a way of guiding surgeons in tumor margins, potentially. We have actually begun clinical studies of patients, and we began those about 18 months ago, in fact. And the first clinical study we're looking at is in stroke, is in ischemic stroke. And this has its own acronym, PUFFINS, which stands for Assessing the Potential Use of Fast Field Cycling MRI in Patients with Ischemic Stroke. Slightly contrived acronym, but PUFFINS, and we even have our little logo with a puffin and an MRI scanner. This is led by NHS Grampian stroke consultant Dr. Mary Joan MacLeod, who works very closely with us. And it is indeed the first clinical study using our 0.2 Tesla FFC MRI scanner. It's actually the first ever clinical study anywhere using fast field cycling MRI. So the patients are identified and give their permission, of course, and are then scanned using FFC MRI on our prototype device, ideally 24 to 96 hours after the stroke. 25 patients have been scanned so far, and we plan to scan 30 in the study. All patients have CT scan when they come into hospital, and many of them also have 3T MRI for comparison. So what the results look like. So this is an early patient in the PUFFIN study from December 2017. This is the CT scan that was obtained on this patient, and it's very difficult to see any pathology in that CT scan. However, when we placed the patient in our FFC MRI scanner, and we took an image at its full field of 200 millitesla, you don't see much there. This shading actually at the bottom is due to an imperfection of the RF coil. That's not pathology. But the pathology can be very clearly seen in the 2 millitesla FFC scan. So that's at 0.002 Tesla evolution field. And although the image quality is not great because we've made that's an early version of the RF hardware, nevertheless, you can see very clearly this region here, which is the region of the stroke-affected brain tissue. And that's without any contrast agent. That's inherent endogenous contrast. It's T1-related contrast at ultra-low field. Because by switching to ultra-low magnetic field, and this really is ultra-low magnetic field, that maximizes the T1 contrast. So we were really excited to see that in just the 4th patient that we'd studied in this group of patients. A more recent patient study. So these are the conventional imaging studies of this patient. So there's CT, and you do see some pathology at the back of this patient's brain in CT. You also see it in 3 Tesla FLAIR T2 images and in 3 Tesla diffusion-weighted imaging studies. You also see some pathology at the back there. When we used FFC MRI, you can see now the image quality is much better. There's the 0.2 Tesla scan. You can see some differences there. But again, when we switch the scanner to 2 millitesla and even 0.2 millitesla, that's 200 microtesla, that's 4 times the Earth's magnetic field, incredibly low field. Again, the contrast just jumps out between the stroke-affected tissues and the normal brain tissues. So that indeed we found very exciting when we got these results. You might say, well, okay, the stroke is already being detected by 3 Tesla MRI. Why do you need a new method? So there are some answers to that question. First of all, 3 Tesla MRI is not done routinely in stroke patients for a number of reasons. One is the availability of MRI. At least in the UK, it's not necessarily that easy to get an appointment, if you like, or a slot for the patient to be scanned quickly after admission. Also, there's the fact that it is very high field MRI, so potential hazards there in case the patient might have implants of any sort. Also, these methods, especially diffusion-weighted imaging, is rather difficult to set up and time-consuming to do the scan. So FFC MRIs is, in contrast, a very low-field technique, so any hazards due to ferromagnetic implants are much lower. It's also rather easy to set up. There's nothing special about these scans. They're just T1 weighted scans using inversion recovery, albeit with field cycling. So very easy to do, very easy to set up, no special setup involved, and no contrast agent is needed, and they're done rather quickly as well. Coming on to the next clinical related study, this is back to the breast studies. So we obtained ethical permission to study to study volunteers using our scanner to study the normal female breast, and we did this both to determine the normal appearance of breast in FFC MRI, and also to determine any changes that might take place during the menstrual cycle. We wanted to see if there were changes in the appearance of breast using FFC MRI during the menstrual cycle. And we wanted also to develop an optimum protocol for scanning, which involved choosing the magnetic fields that we would scan at. So if you remember back to the ex vivo breast cancer studies, I showed previously these curves of the relaxation rate 1 over T1 as a function of magnetic field strength, and I showed that the curve for normal tissue was very different to the curve from cancer and that from peripheral tissue. So when you make measurements like this on small tissue samples, you can afford to measure at maybe 50 field strengths, as was done here, because those measurements can be done quite rapidly. It only takes maybe 10 minutes to record one of these curves. When it comes to imaging, imaging is inherently a slower process, so we cannot image at 50 field strengths. We have to choose 4 or 5 field strengths, and we have to make an intelligent choice of those 4 or 5 field strengths so that we can nevertheless measure in our images when we come to image patients, so that we can differentiate between the shapes of these curves. So we designed a protocol in order to do that. And this involves choosing 4 magnetic field strengths. So the first one is at high field for our scanner, 0.2 Tesla. The second one is at low field, 2 millitesla. And the third one is at this break point here, where these 2 linear sections change, where the slopes change, and the inflection point. And then the fourth field is at one of these quadrupolar peak magnetic fields. So this was the protocol that we developed, and these are examples of volunteer breast images. They're color-coded for the 1 over T1, the R1 parameter, relaxation rate parameter. And those are images at 2 millitesla, 21 millitesla, 200 millitesla, and 65 millitesla. You can see structures appearing in all of those, and you can see that the R1 values, the relaxation time values, are different at the different magnetic fields, as you would indeed expect them to be. So this is as a precursor for making measurements in patients. And indeed, we can analyze those images to form parametric images. So parametric images associated with the shapes of the relaxation curves. So this is still in normal volunteers, so we're not seeing any pathology here. But this parametric image shows the high frequency slope component. This is the low frequency slope component. And this is the quadrupolar peak amplitude from the bumps in the curves. So again, this is a precursor to clinical studies. We have very recently obtained ethical permission to start imaging breast cancer patients. We haven't imaged any patients yet, but we plan to start imaging patients in the very near future. Within the next month, we'll start imaging patients with breast cancer, and we'll use all these methods. We'll use the protocol we've developed, and we'll investigate the use of these parametric images in order to highlight the tumors in patients. So, some conclusions. FFC MRI really is a new imaging modality. It's based on MRI, but it's MRI not as we know it, Jim, as they might have said in Star Trek. It does provide new information that's invisible to other modalities, including MRI. It indeed generates new kinds of image contrast, which indeed is endogenous because no contrast agents are needed. That's another advantage. It uses low magnetic fields, so it's safe and applicable in emergency situations. It is indeed unique to the University of Aberdeen. Patient studies are underway, as we've heard, so the stroke study is well underway. The breast volunteer study is underway, and breast cancer study is soon to begin. We've also actually recently started a study on brain cancer patients, and we have imaged 2 patients already. And an osteoarthritis study is being planned right now, and we're in the process of developing an ethics application to study those patients. Of course, this was, as you'll appreciate, this was not just my work by any means. So we have a fantastic team of scientists and engineers working on the project. We have a very enthusiastic medical team. Actually, the medical doctors at Aberdeen Royal Infirmary are literally queuing up to work with us on FFC MRI. In many other specialities, in addition to ones I mentioned, the medics are very keen to start using this technology. And we have a very efficient administration team as well working on the project. We have many external collaborators, some of whom are mentioned there. Those are present and recent funders. Most of our funding at the moment actually comes from the European Union, of which I'm a big fan, not to get political anyway, but we are leading a Horizon 2020 project with partners in those locations around Europe. This has been a 4-year project, and we're now in the final year of this project. And that's the final slide. Have you guessed what it is? It's a cycle in a field. And those are our websites, and thank you very much for listening.